And one of the most important things we're going to start doing is seeing how the derivative and subsequent derivatives are going to impact the shape of graphs. So in this section, we're going to talk about increasing and decreasing functions, and then something known as that first derivative test. So this will be a way to kind of help us classify local maxes and mins. So the increasing, decreasing is going to kind of lead into whether something is a local max or min. So we're going to start with, what does it mean for a function to be increasing? And what does it mean for a function to be decreasing? So first, a function f is increasing on an interval I if for any two numbers, x1 and x2 in that interval, the y values are getting larger whenever the x values are getting larger. So think of 1 and 3 as your x values. Your function evaluated at 1 should be smaller than your function evaluated at 3. So my y's are getting bigger as well. If we want to deal with decreasing, it's the exact opposite. So a function f is decreasing on an interval I if for any two numbers, x1 and x2, those y values are getting smaller whenever the x values are increasing. So it's that opposite relationship. Okay. So how is this going to relate to a derivative in any way, shape, or form? Well, since the derivative represents the slope of the curve at some point x f of x, the slope of that tangent line is telling us kind of where that function is heading. So it's basically giving us the direction in which the curve proceeds. So ultimately, we can expect some information about the derivative is going to tell us some properties about the function. So what I want to do is I want to look at this particular function. We'll call this f of x. And we're going to look at the tangent lines at a few particular points. So if we look right here at these two I have highlighted, 1 and -1, if I were to draw a tangent line at both of them, they're going to be horizontal. Here, So let's take a look at a particular function just so we can kind of get some ideas about what the derivative is telling us in terms of the properties of our graph, and also maybe kind of seeing how it relates to local maxes and mins. So if we look at these two values of x, 1 and -1, if I look at the tangent line at -1, it's going to have a horizontal tangent. If I look here at +1, it's got that sharp turnaround, so there's no tangent here. So 1 and -1 are critical numbers, and they also correspond to extrema. Now, if I look over here, my y values are getting bigger and bigger up to this point. So my function is increasing. Regardless of the point I pick, if I go ahead and draw the tangent line, all of these tangent lines are going to have positive slope. And if the slope of the tangent line is positive, that means my derivative is positive. So on this left half, my graph is increasing. My derivative is also positive. Same thing over here. My y values are getting larger and larger and larger. Regardless of the point you pick, if you go ahead and draw that tangent line, it has a positive slope. So over here, my graph is also increasing. My tangent lines are positive my tangent lines have positive slopes. That means the derivative is positive. If I move in the middle, my graph is falling between -1 and 1. And if I look at any of these points and I go ahead and look at the tangent line, they are falling and my slope would be negative. So when my graph is decreasing, my derivative is going to be negative. So this is just a single example that kind of shows you what's happening, but that's exactly what our increasing, decreasing test guarantees us. And I'm going to actually show you the proof of this because it's a really nice application of mean value theorem. So we're going to let f be differentiable over an open interval I. If my derivative is positive for all x in the interval, then my function is increasing over that interval. So my derivative being positive guarantees that my function is rising because those slopes of tangent lines are rising. Okay. If my derivative is negative for all x in a particular interval, then my function is decreasing over that interval. So I do want to show you the proof, and I'm just going to show you the proof of this one. If my derivative is positive, I get increasing. Because really, the same kind of thing is going to happen for this second one. It's just a slightly different result that you get at the end. So what I want to do is, purely because my derivative is positive, I'm going to go up here and show that my y values are getting larger and larger and larger. So what we're going to do is we're going to let x1 and x2 be any numbers in the interval, and I'm going to say x1 is smaller than x2. Doesn't matter the order you pick it in. Now, because my derivative is positive for all x in my interval, I'm guaranteed f is differentiable on this interval. And because it's differentiable, it's continuous there. And those are the two hypotheses I needed for the mean value theorem. So, by mean value theorem, there exists a number c inside this interval x1 to x2 such that the difference in y values is equal to the derivative times the difference in x values. So I'm going to call this equation star just to make my life a little bit easier in a second. But what I want to do is I want to dissect what's really going on over here. My derivative, positive, that's my initial given hypothesis. My derivative is greater than 0. x2 is bigger than x1, so this quantity also going to be positive. We have a positive number times a positive number. That means this thing on the left also has to be positive. Okay? So we're going to put that into words now. Since the derivative is greater than 0, and since x2 is greater than x1, meaning their subtraction is positive, the right-hand side of this equation is positive. So what we get then is what's on the left also has to be positive. So the difference in the y values has to be positive. Adding f of x1 over, I now am guaranteed that my y values are getting larger and larger and larger. So this is exactly what we needed for increasing. So I get my function is increasing. If I want to do that second case and my derivative is negative, this would be a negative number times a positive number. The only thing that would change is this would be negative. So really that second part can be shown in a similar manner. Okay? So this is why that mean value theorem is really useful for us, because this increasing decreasing is really nice. And increasing decreasing tells us a lot about our properties, but if you look here, we went from increasing, stopped, to decreasing. We have a local max here. When we're decreasing, stop, increasing, I have a local min there. So being able to kind of gauge what properties are happening for the function or for the derivative helps us classify these critical numbers and helps us classify them as local maxes or mins. So it's really, really, really useful for us because we want to find these maxes and mins. Okay. So let's get some practice first just with increasing and decreasing. We're going to work with this polynomial function, and we're going to work with it pretty consistently across a few different examples in later sections as well. We've got 4x cubed plus 3x squared minus 6x minus 6. We want to go ahead and find the intervals of increase or decrease. So pretty much I want to see where is the derivative positive, where is the derivative negative. So to be able to do that, I need to go ahead and take the derivative. And I'm just going to apply power rule bunch. So bringing the 3 down would give us 12x squared. Bring the 2 down to get 6x minus 6. Everything has a 6 in common, so we can factor that out to get 2x squared plus x minus 1. And then that factors really nicely into 2x and x, make this a plus 1 and this a minus 1. Okay. So I need to find my critical numbers, so where this derivative is equal to 0. And I'm testing, is this thing positive or negative? This is what you spend so long doing in college algebra, pre-calculus, trig. You're seeing where a function is positive, seeing where a function is negative, going through and solving all those polynomial inequalities. So I want to pick out some key points, which are the critical numbers. So that would tell me my derivative is equal to 0 or undefined, which doesn't happen. So either 2x minus 1 equals 0 or x plus 1 equals 0. So this tells us 2x equals 1, or one important number for us is 1/2. Another important number for us is -1, okay? So these are where my derivative is exactly equal to 0. Those are going to be the numbers I use on my number line. And I'm testing to see what is happening with my derivative. Is it positive or negative? So I'm going to break it down to my -1 and my positive 1/2. And we're left with 3 different intervals, 1, 2, and 3. I want to go ahead and I want to pick any number that falls in here, plug it back into this derivative. If that number is positive, then this interval is always going to be positive for my derivative. If it's a negative number, my interval is always going to be negative. That's why we need to find those critical points of where it exactly equals 0, because that's going to be our key point. It can split off and change signs. So from the first interval, we can pick anything we want. I'll go ahead and pick -2 because that falls in here, but you can pick -3, -4, whatever you want. And we're going to plug this into the derivative. And you can use any one of these 3 pieces, doesn't matter. I'm going to go ahead and do the one at the bottom because it's going to be a little less work for me. So if I plug -2 into the derivative, that will be 6. 2 times -2 minus 1, and -2 plus 1. That will be positive 6, -4 minus 1, and then -1. You can simplify this number, but it's a negative number times a negative number. That's positive times a positive. Overall, this thing is greater than 0. So in interval 1, my derivative is always going to be positive. So that means my function is increasing. Okay. Now I want to test something that falls between -1 and 1/2. If you can pick 0, always pick 0. Plugging this into the derivative would give us 6. 2 times 0 minus 1, 0 plus 1. So that's going to be 6 times -1 times positive 1. This thing is definitely going to be negative. So on interval 2, my derivative is negative, which tells me my function is decreasing. And then finally, in interval 3, you can pick whatever you want. 1 falls in there, and that's a nice number. So if I plug that into my derivative, that'll be 6. 2 times 1 minus 1, and 1 plus 1. So 6 times 1 times 2. This is definitely positive here. So my derivative is positive on this interval, which means it is always going to be increasing. So utilizing all this, my function is increasing on the interval from -infinity to -1, and then also from 1/2 onward. And it's decreasing between -1 and 1/2. And now I've set this up in a really nice way because this is actually our next test, the first derivative test. Your function is going up, 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 stops, comes back down. This would classify as a local maximum. So that graph going up, come back down. Same thing here, connecting these two, that classifies as a local minimum. So this first derivative test gives us another way now to classify things. It's not extreme, it doesn't have to be the absolute max or min, but it gives us that local stuff, which is what we want. So suppose that c is a critical number of a continuous function. If your derivative changes from positive to negative around c, then you're guaranteed that a local max happens at c. So just like this case, your derivative goes from positive to negative, creates that shape of a local maximum. For the second part, if it goes from negative to positive around c, then it'll be a local minimum. So just like over here, goes down, comes back up, you have a local minimum at 1/2. If the function doesn't change signs, then it's not a local max or a local min. So really this follows directly from our increasing and decreasing tests. And I'll show you pictorially in all of these cases. Okay. So let's take a look at this example. Right here, I definitely have a local maximum. And if you go ahead and draw the tangent line there, it is flat. So f prime of c does indeed equal 0. And if I look at any point over here, every time you draw a tangent line, it is positive. So on this side, my derivative is always positive. On the right-hand side here, no matter where you pick a point, the tangent line has negative slope. So my derivative is negative. So pretty much what happens is you have this flat tangent line here where the derivative is equal to 0 and your graph is increasing and switches to decreasing. Okay. If I look at this next point, that is definitely a local minimum. The derivative does indeed equal 0. And then over here to the left, you've got tangent lines with negative slope. So the derivative is going to be negative. On the right-hand side, you have tangent lines with positive slopes. So the derivative is going to be positive. So you've got this point where your function is decreasing, stops, and increases again. Okay. Now this last one, there's no local max or min here because on either side it's getting bigger or smaller. It's not creating that shape of a max or min. But if we look exactly at c, you do have a flat tangent line. So the derivative evaluated at c does indeed equal 0, and it's a critical number. The problem is if I pick any point over here, the tangent line is positive. And if I pick any point over here, same thing. Tangent line is positive. So on the left half, the derivative is positive. on the right half, the derivative is positive. So it's not changing signs. So you've got this flat tangent here, but you're going up and you continue to go up after this. So I don't create that shape of local maxes or mins. Shelby, go.
Shelby, come here.
No, Macy.
Macy, you can't go.
Macy, come here. My pretty girl, lay down. So let's take a look at that last function we just did. We want to find the local max and min values. So we've already gone through most of this process. Since that derivative was 6 times 2x minus 1 times x plus 1, the critical numbers are x equals 1/2 and -1. And we've seen that when you go to test the derivative on an interval, on interval 1, it's positive, and on interval 3, it's positive. So your graph is increasing. On interval 2, it's negative, so your graph is decreasing. So ultimately, around -1, we switch from positive to negative. So f prime changes from positive to negative around x equals -1. So a local max occurs here. So when you're doing your interval testing, drawing these arrows about increase or decrease really helps you classify those local max or mins. Now specifically, we're asked to find local max and min values, so we want the y values. The x coordinate is -1 where it happens at, but the local max value is the y value. So if we plug this back into the original function, that would be 4 times -1 cubed. So plugging -1 into this point, anything that's an odd power of x will change sign. That would be 4 plus 3 plus 6 minus 6. Which is -1. This is our local max value. Now, around +1/2, we switch from negative to positive on our derivative. So f prime changes from negative to positive around x equals 1/2. So a local min occurs here. Again, to get the local min value, you would plug that back into your original function. So if you do that, you would end up getting -5/4. So this is our local min value. Okay. So be careful when you're reading the instructions. Does it ask for where they occur, or does it ask for the local max or min value? If it's asking about the value, it's always corresponding to the y component of the function. So I just have 2 more examples because it's going to be best the more practice you can get with these things. We're going to work with the function 2x cubed minus x to the 4th, and we're going to do 2 different things. First, we want to find the intervals where f is increasing and where it's decreasing. So we need where the derivative is positive and where that derivative is negative. So repeating the same process, we want to go ahead and start by finding critical numbers. This will be how we break our number line. So this is where the derivative is equal to 0 or where it's undefined. Okay. So I need to go ahead and take my derivative. Applying our power rule will give us 6x squared minus 4x cubed. We can go ahead and take a 2x squared out, and that will leave us with 3 minus 2x. This is never undefined, which is nice. So I just want to go and set this equal to 0. And so that tells us either 2x squared is equal to 0 or 3 minus 2x is 0. The only way 2x squared equals 0 is if x equals 0. Solving this gives us 3 is equal to 2x, or 3/2 is equal to x. So ultimately, x equals 0 and x equals 3/2 are the critical numbers, which means these are our possible local maximums. So we need to see where this is increasing or decreasing. We're going to create a number line with these values and test our intervals. Okay. So I'm going to go ahead and create a number line. And we're testing where is the derivative, which remember is 2x squared times 3 minus 2x is positive or negative. And we have 2 key points, 0 and 3/2. So again, this splits my number line into 3 separate intervals. Okay. So picking something from interval 1, you could pick -1, -2, whatever you want. But you want to plug this into the derivative. So that would be 2 times -1 squared times 3 minus 2 times -1. -1 squared is +1, and that would be 3 plus 2. This thing, I don't need to do any more work. It is definitely positive. So my derivative is positive here, which means immediately that my function is going to be increasing on this interval. Okay. Now, picking something from interval 2, a little bit more difficult to find a number. That's between 0 and 1.5. So let's pick 1. Plugging that into the derivative would be 2 times 1 squared times 3 minus 2 times 1. So that's 2 times 1 times 3 minus 2, which is 1. This thing is definitely positive. So again, my derivative is positive on this interval. And again, that means it's increasing. Okay. Now I want to pick something in interval 3. Let's go ahead and plug in 2. If we do that, that'll be 2 times 2 squared times 3 minus 2 times 2. So that's 2 times 4 times 3 minus 4. 3 minus 4 is negative, so this thing is negative. So my derivative is negative in this interval, which immediately tells me it is decreasing. So for my function, we are increasing from negative infinity up to 3/2. You can write it as 2 separate intervals from negative 3 to 0, 0 to 3/2, but just goes through that point. And then the graph is decreasing from 3/2 onward. Okay. Now the second part asks us to find and classify any local extrema. Well, we did that really. Go ahead and just bring this right down here. There is no change at 0. I just keep going through that point and continue up. So that means nothing happens at 0. So there's no change around x equals 0. So it is not a local max or min. Now, if we look here, my graph is going up, stops, and comes back down. That means this is going to be a local max. So there is a local max at x equals 3/2. Okay. And if you want the local max value, is you plug 3/2 into your original function. So if you go through and do that, you would see it would end up being 27/16. Okay. So we need to get really, really, really comfortable with this. You are going to be doing a lot of number lines and a lot of interval testing, which is why it's really emphasized in a lot of your other classes. It's a really important concept for us. You're going to be solving where things are positive, where things are negative, because that's telling us about properties of the function. We also have a second derivative, which is going to tell us about something called concavity. So we're going to see that really soon too. So we're going to get more practice over and over and over again in all of these sections. So for that reason, I'm not going to do another one just like that. We're going to go ahead and work with a graph of a derivative. So this is the derivative of our function, and we're going to answer a few parts. Okay. First thing we want to do is we want to identify any critical numbers of our function. And again, it is a graph of the derivative. So if I want critical numbers, that's where the derivative is equal to 0. So I have quite a few spots that happens for. -2, -1, 1, and 3. All of those values, my derivative is equal to 0. So the x values this happens for are -2, -1, 1, and 3. These are the critical numbers. Okay. Now, we also again have the graph of the derivative. We want to identify where the derivative is increasing or decreasing. So I need to figure out where this graph is positive and where the graph is negative. So remember, f prime of x being greater than 0 tells me about increasing, and f prime of x being less than 0 tells me about decreasing. So my derivative is positive from negative infinity up to negative 2. Then from negative 2 to technically positive 1. But really you can kind of just keep going. So the other interval it happens for is from negative 1 up to 1. And then from 1 to 3. That's where our derivative is positive. For decreasing, that'll be where it's negative, which happens between negative 2 and negative 1. And then from 3 onward. So from 3 to infinity. So bringing those down here, this is where our derivative is positive and negative. So ultimately, our graph is increasing over the interval negative infinity to negative 2, negative 1 to 1, 1 to 3. But if you just did negative 1 to 3, that's fine. And then it's decreasing where that derivative is negative. So exactly on those same intervals. And then finally, we want to utilize this graph to determine the x values where f has a local maximum. So I'm going to first regraph this here just so we don't have to keep scrolling back up. We're pretty much applying the first derivative test without knowing anything about the function. But negative 2, negative 1, 1, and 3 were those critical numbers. Our graph of the derivative is positive on this interval, positive here, and negative inside of here. So my graph is increasing, 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 decreasing, decreasing. So applying that first derivative test immediately tells me this is a local max. This is a local min. This is absolutely nothing. And likewise, we're going up, coming back down. This is a local max. Okay. So we have a local max at x equals negative 2 and positive 3, and a local min at x equals negative 1. So don't get confused. It's really common that people want to pick these points because it looks like, local maxes and mins on here. Be very, very careful because, again, this is a graph of the derivative. So that is it for our increasing and decreasing test and our first derivative test. We will pick up and we will learn about some more properties and more applications of derivatives next time.